Hello everyone, my name is Mayank Yadav and I represent you, team researchers from Bennett University. We bring you a detailed analysis of different types of matrix decomposition techniques. So first of all, what is the need of decomposition techniques? Matrix decomposition in numerical algebra typically serves the purpose of restating some given problem in such a way that it can be solved more readily. Also in machine learning and statistics, we often have to deal with structured data, which is generally presented as a table of rows and columns or a matrix. A lot of problems in machine learning can be readily solved using machine.
Matrix decomposition techniques.
So here is a detailed analysis of some of such techniques by my friend Shalin Agarwal and Anshul Trivedi.
Hello guys, I'm Shalin and now I'll be taking you through some of the code which we use to implement the various decomposition methods and how we compare them. First, we import the necessary libraries needed for them, and I've also set the numpy's random seed to be constant so that we could reproduce the matrices perfectly every time we just generate a random matrix. These are our time functions which we use to measure all the time differences and all. This is how I implemented my LUT composition. It's just basic and it's just basic SciPy's version. It's just Doolittle algorithm. And this is the Gaussian LU which we normally implement when we try to solve the LU decomposition using a pen and paper. These are all the QR functions. I've used two functions. One is from SciPy's QR implementation and there is a NumPy implementation. And these are all just the values I used. Now, after taking you through all these different codes, you could get that same in my repository, which I have linked in my document. Let me just go through the results which we obtained. After going through the results, this is the R2 score for the four different functions which I just compared. So as you can see, for the eigenvalue decomposition, the score was a perfect one, which is not really indicative of its real world performance, since the eigenvalue after reconstructing the matrix was returning some complex values. We couldn't really compare it, so I used an absolute function which I just used the real part of them. So the functions were really skewed, the values were really skewed, so that's why it's a perfect one score. Or the other functions we can see interpolative does the best job, while rest are not really that good as they tend to negative. Now after value function, this is the time function. As we can see, as the value of n increases, the time will definitely increase, but we can see for the eigen the time increases the most. So we can conclude from this that like eigen is not really a very efficient way of decomposing these matrices. Hence that's why we don't really prefer using eigen in real world applications where we have like a million or so entries, a million cross million matrices or something like that. So these are all just the different plots. This is the basically all the summary of the function. You can get a mean square data. We plotted them all just for the sake of ease. Now let me go towards the QR functions. QR and Cholesky, these are all the implementations using NumPy and SciPy, different implementations of different functions. This one is for the Cholesky function. As you can see, mean square error for both of them are exactly the same. That's why we can't really distinguish between both the lines. But for the like mean absolute error and like R2 score or time, we can see a lot of difference between them, which is as we can expect since these are like using different type of algorithms or implementing different types. This is a total summary of all my functions. As you can see, like you can just see like eigen is like really inefficient, really bad at implementing matrices. Even that is for the 1000 cross 1000, but even then for the 1000 cross 1000 matrix, it's just going forward upwards of 1 second. That's really not optimal for eigen. Rest all are like kind of similar, like just belonging there. So yeah. Thank you guys for watching. Let's proceed forwards.
Hello friends, my name is Anshul Trivedi and today I am going to speak about implementation of SVD. So SVD is a very famous algorithm for decomposing a matrix. So we decompose a matrix into three matrices, use sigma and V transpose. So I've compared the NumPy and the SciPy implementation. This is the divide and conquer approach, and this one is the general rectangular approach. This is the mean absolute error versus dimension plot, and this one is the mean squared error versus dimension plot. So FunkSVD is also a very famous algorithm. It is basically used for recommender systems. In it, we find the latent factors of user matrix and item matrix. So in real life, the data is almost 95% null. So to deal with it, FunkSVD finds a way to compute latent factors even when the data is not present. So in this plot, I have taken the matrix dimension as constant of 200 by 200, and you can see that as the latent factors increases, the time taken to apply the algorithm is also increasing. This is the time versus dimension plot of FunkSVD, and this is the mean absolute error versus dimension plot of FunkSVD. Similarly, this is the mean squared error versus dimension plot of FunkSVD. So sparse SVD is similar to normal SVD. We factorize a matrix into U sigma and V transpose. However, it is basically used to operate on sparse matrix, and it has fast implementation. It can also be used for recommender systems. So this is a time versus dimension plot of sparse SVD. So you can see that it is taking less time than normal SVD algorithm. However, it is giving more error, as you can see from the mean absolute error versus dimension plot and mean squared error plot. I've taken also the example of a sparse matrix and applied sparse SVD on it. So this is a time versus dimension plot, and this is the mean absolute error plot. So randomized SVD is an efficient way for decomposing any large matrix with a relatively low rank. It is also faster than normal SVD. So as you can see that it is taking less time than normal SVD algorithm. However, similar to sparse SVD, it is giving more error, as you can see from mean absolute error versus dimension plot and mean squared error versus dimension plot.